Hello everyone, this is the part 3 video in our series in which we discuss doing open domain question answering using dense retrievers. In this particular video we will discuss about ORQA, which stands for Open Retrieval Question Answering. The video is set up in 4 different parts. First we'll discuss a little bit about the paper in which this task appeared. Then we'll talk about the task setup and then the architecture and the cost function that is used in this task. So talking about the paper, ORQ as a task first appeared in this paper called Latent Retrieval for Weakly Supervised Open Domain Question Answering. So this was the first paper in which the retriever was trained end to end along with the QA model using the question answer pair. So this paper has majorly 2 very new interesting ideas. First one is inverse closed task, which is like a pre-training method for building retrievers, which we will be discussing later in the series when we talk about how to build retrievers, dense retrievers. And the other one was ORQA. And we will be discussing this paper in such a way that it's very easier to understand the code also, because there are some details here which are a little bit different when you try to see in code, and then you might be surprised, okay, what is happening here. So we'll talk about this entire paper in a way so that it's easier to understand the code, for which I'll also include the link in the description. So first, talking about the setup. In our previous videos, I gave a general architecture of what exactly happens in an open QA. So just a quick reminder here. So in open QA, you are given a question Q, and then this question is passed to a retriever. Now this retriever has access to a text corpus. Generally it is Wikipedia, or it could be some other text data set. So the idea is that this retriever will search the entire Wikipedia corpus and then give us some documents, let's say Z, which the retriever thinks can answer this question and can help in answering this particular question. So the question and the retrieved documents are then passed to a QA model, and that QA model after that predicts the final answer. We use the predictions of the QA model to train it using marginal log likelihood, as we discussed in the last video. So that is the basic architecture. So talking about basic setup here. So first of all, we'll have to discuss about the text corpus. So in the paper, they used Wikipedia as the text corpus, and so the idea is that, let's say there is one particular article in the Wikipedia about rocks. So since we don't really have very good paragraph tokenizers with us, and generally if we are retrieving paragraphs or certain text blocks, it would be really nice that we can get the actual paragraphs that are there in the Wikipedia text. But that problem is, I think, not solved till now, a very good paragraph tokenizers. But we have very good sentence tokenizers. So what we do is we join all the text so that it's one big blob of text, and then we get all the sentences so that we have all the individual sentences that are present in the text, and then we create blocks such that each block has a maximum of 288 word pieces. So just a little bit background on what word pieces is. So word pieces are the tokens that are built using the byte pair encoding algorithm, and they don't necessarily mean the traditional word tokenizers that we had, like each word will be a separate tokens, and for each of the possible words we'll have a separate vocab or an embedding in the token embeddings. When we do word pieces, the word itself can be split into subparts based on the usage of and the total usage of the tokens in the entire text corpus. So the word like democratized can be split into different ways. It could be democrat anized, and it could be democratanized. So when we do word piece tokenization, it's not necessarily that we get the exact number of words that are. We won't know what is the total amount of tokens we'll get, because it will depend on what is the word is, and if there is any space in front of the word, or if there any special character after the word. So that was about word pieces. So what we do is, now that we have all the sentences here, we convert each sentence into its respective tokens, and then with each token, with each new sentence, we see if the tokens present in this sentence with the addition of this sentence has gone above 288. If so, then the next then this sentence is set as the starting of a next block. So what happens is that you have a limit of paragraphs whose token length will not cross 288. And when I first tried it, it seemed it might not work really well, but when you actually test it, it's a pretty good standardization when it comes to building paragraphs when you don't really have a very good paragraph tokenizer with you. So the authors did this entire thing on the entire Wikipedia corpus, and they got almost 13 million blocks of text. Yes. So in the setup in this paper, whenever you ask a question like continuing on the original question, what are the total number of rocks, the retriever will search the entire 13 million blocks to finally get some top K or top K documents in which the answer could be present, and then you will get an answer from the QA model. So that is why OpenQA is very interesting, because you can give it the possibility of entire human text that is out there, and the model won't be really good, but yeah, it will be able to learn something and how to look, how and where to look the answers. So that was about the text corpus that is used. Next, we have to understand what is a possible answer derivation. So in our case, we identify an answer as a pair of the block and the span. So let's say out of 13 million paragraphs that we just created, our answer is present in the block number 100, and the exact answer span is from let's say 10 to 15. So what this mean is, let's say we have the 100th block here talks about, let's say, presidency. Okay, so we convert the entire block in tokens. We will have the tokenized version of the block, and in that tokenized version, from token number 10 till token number 15 will comprise the answer string. So, and before we go any further, let's talk in a little bit more detail about spans. So a span is represented by a start token number, and an end token number. So here, if you see, the span from the start token here was 10 and the end token was 15. And let's take one more dummy example. So let's say we have a sentence, let's say, I am Akash. Okay, and these are so there are total 3 tokens here, 1, 2 and 3. So a span would represent, let's say, if the answer string was from token number 1, 3, or the answer string is from 1, 2 or 2, 3, and in case of single word answer, it could be something like 1, 1, 2, 2 and 3, 3. So if you see that when we have the maximum span length as 3, there are six possible variations of what the spans, different spans that are possible for that particular maximum span length. So the idea behind ORQA model in this case is like whenever we get a question and a retrieved paragraph or a block here, the notification, the nomenclature is a little bit different in this paper. So sometimes I might uh, write B as Z, but they both will represent a retrieve block. So in a QA model, whenever you get a block, the job of the QA model is to predict between all the possible spans, let's say 3 comma 3 2 2 2 1 comma 3. So the job of the model is to predict which of these span is the correct answer. So let's say if I am Akash, the entire answer string was I am Akash, which would never be, because that doesn't sound like an answer string. But let's say if that was the answer, then the job of the model is to predict the highest value for this particular span value. So I hope the concept of spans and how the span is used in this model is much more clear. Next, in setup, we have to talk about the scoring function. Now, scoring function is not the same as loss function. This is something that the model gives as a score to a pair of B, S and Q. So when there is a retrieve block B and a given question, for a particular span, what is the score that the model gives? So if you look here, when the model is predicting some values for each of these spans, it must be giving it some values like some logits. So 2.3, 4.5, minus 10.9, something, right? So what is this value? This is the exact value that the model gives, the logits that the model give to a particular span. So how is this value calculated in the model? So we represent this as SBSQ, and it shows how good the particular answer as the span is, how good this particular span is as an answer. So SBSQ consists of two parts. It is equal to S retriever given B comma Q plus S reader from B as Q. So this part is something which comes from the retriever, and this part comes from our QA model. This might seem a bit different, but if you remember from our last videos, we usually do when we have pz comma x times p of y given z comma x, we take a log of these values, and this becomes log of the probability of that retrieved block plus the log of the target answer that the model gave given the retrieved block and the input question. So this is the same thing here. So this represents the probabilities, the log of the probabilities that we get from the retriever, and this represents the log of the probabilities for the answer that we get from the QA model. Another important thing in the setup that we have to discuss before we move on to architecture of the model is what exactly happens at inference time, right? So how does the model predict which answer to choose? So because in OpenQA setting there is not just one document, right? So there will be, let's say, B1 document, B2 document, all the way, let's say, to BK document, and each of these documents will have some total number of possible spans, like the ones we discussed, right? 1 comma 3, 1 comma 1, 10 to 15, or 15 to 19. So this is something that we'll fix already. We'll fix what is the total maximum span that can be for a particular answer. So let's say if we fix the maximum span size as 10, So there will be no span in which the difference between the start and the end token is greater than 10. So once we fix that, there will be a total list of all the possible spans that we have in that is possible, and then we'll have such a tensor which represents this value for all the passages that are existed, that are there in the retriever, the ones that retriever retrieved. So at inference time, what happens is that as we discussed earlier, the job of the model is to give some sort of a logit or a probability for each span. So the model would have given probabilities or logits here to each of the possible spans here, and the idea is that whichever span in all of these blocks has the highest value, that block and that span will be chosen as the answer at inference time. So how do we write it mathematically? Mathematically, we say that the answer at the retrieved time is equal to text of argmax of b comma s of the scoring function. For this argmax is calculated for over all the blocks and all the spans that are possible. So I hope you understand visually what just happened here in this equation. Yeah, and text here basically represents whatever text of a span s is nothing but the text that is present from the start token to the text that is present between the end token. Yeah, so that brings us to the end of the what is the task setup, right? So you might be thinking, if the setup is so big, what about the architecture and how will things will be there? So yeah, let's dive right into what is the architecture of the task. So as we discussed earlier in the main in a general architecture of the task, so there are two major blocks that are present in the model. One is the retriever and one is the QA model. So we have a retriever and a QA model, and the retriever itself consists of two major parts. So first one is the question encoder, and the second one is the passage encoder, or you can say as the block encoder. And there will be one QA model. So to initialize the model, we start with a pre-trained BERT model for all of these. So there will be a BERT Q model, there will be a BERT P model. So BERT Q model is used to process the question, BERT P model is used to process the passages, and the BERT I think R model is used to represent the QA model. So we initialize each of these components with a pre-trained BERT model, and let's say we get an input question Q. So what happens is that we pass this input question to a BERT model, specifically BERT Q for processing the question. And after tokenization, we know that generally the models will append, like specifically in case of BERT. So let's say if the sentence was I am Akash. After tokenization, they will add a component, they'll add a token here, the CLS token, and after the end of the sentence, they will add a separation token. So in most of the classification tasks, we use the embeddings that are generated for this CLS token as an input for predicting something new. So here also we do the same thing. So we use the embedding of the CLS token here, and we multiply it with a trainable weight, which is WQ here, to get the final representation for a question. So mathematically, if we write, so the final representation of the question represented as HQ is nothing but the WQ times the representation of the question, the representation of the CLS token after passing that question through the BERT model. So this is the representation of a question. Next, what happens with passages? So again, with passages the same thing happens, but there is one important thing that we have to keep in mind. So for when we are processing a passage, we don't do it every time when a new question appears. So because we have 13 million of them, right? So that won't be that doesn't make sense to do it each and every one of time. So what happens is, similarly, let's say there is a one single block here, so we pass this block to our BERT which one, BERT P model. We'll pass it to BERT P model, and we'll take the representation of the CLS token, multiply it with a trainable weight, which is WB here, and that's how we get the representation of a block. So written in an equation form, HB is equal to WB times BERT's, when we pass the block to the BERT model, and the representation of the CLS token there. So what happens in actual practice is that we calculate this all these values for all the 13 million blocks beforehand. We don't usually do calculate these values individually for each of the blocks individually, as I said. So what happens is that we have the HB1 here as a vector here, and then similarly we'll have an HB2 for the vector for all the HB 13 million. Yeah. So what happens next? So now we have to find how good this HQ and HB, how good they are for each other. Like, how do we know that the answer for a particular question is present in that block? So to do that, to get the retriever score, the S retriever given a block and a question, which came here, if you see, the first part of a scoring function comes here by the dot product of these values, the dot product of HQ and HB. So in practice, what happens is, because this we have specialized libraries which do this for us, and I think one of them is FAISS. So at runtime, it will whenever a new question arrives, the question encoder will create the HQ for it, and once we have the HQ, we already have the HB for all the 13 million all the 13 million blocks, and it, using specialized libraries, we quickly calculate the S retrieval for each block. So this value will be calculated for B1, Q, B2, Q, and then we take so our QA model can't process the entire 13 million paragraphs at the same time, right? So what we do is we choose the paragraphs which have the highest highest S retrieval score here. So in practice, we'll shortlist some size of some fixed size of paragraphs that will be passed to the QA model. So here that parameter is represented as reader beam size. So what we'll do is we'll take some top 10 or some top 50 paragraphs which had the highest value for the dot product between the HQ and HP for them. And yeah, before we go ahead, there's one important thing that we have to discuss here, that we don't train the parameters in our passage encoder. Later developments in paper like Realm, they started training the passage encoder parts also, but since this was the first task and they were trying to keep changes to the minimum. I guess these encodings were fixed for entire process. So the idea was that in retriever only this part, the question encoder here will remain trainable. Okay, now that we have discussed what happens in the retriever, let's talk about the reader component. So as we discussed, so we calculate the S retriever score for all the 13 million paragraphs that are there in our text corpus, and then we select the top 10, 20 or so. So what happens in the QA model? So we pass all the retriever beam size paragraphs, something like this. So the question, CLS token, the question, the separator, and then the first block will be sent like this. And similarly this will be for B1, and similarly this will be for B reader beam size. It will be same, but here it will just be B2. Similarly here it will be B3, and here B reader beam size, and we pass this entire thing to our QA model, which is BERT in our case. So when we do that, we get a representation of all these paragraphs that we sent in a tensor of shape reader beam size, the sequence length, and the hidden size of the BERT model. So this is the representation that we get from the model. Now sequence length here will depend on the kind of the block size, that is the actual block size that is passed to the model. So let's say the maximum block size here, based on your strategy of tokenization, it will vary, but it depends. This is a variable thing and it's not fixed. You can keep it fixed, but I think most of the people watching this video will already know what sequence length means here. Okay. So what we have here is the representation for each and every token that is present in the input sequence. So let's say when we sent CLS and question here, what are the same question that we have been talking till now in the series, what are the total number of rocks and separation token, and then let's say there are total of 110 rocks, blah blah blah, some separation. So what we have till now is the representation for each of these single tokens here from the model, right? But what we need to find out is what are the chances of each of these token as being either the start token or the end token. So what we do is, to do that, we multiply our original representation here by a matrix which converts it to the size of I'll just write reader beam size as RBZ from now on, just for the sake of time. RBZ sequence length and 2 into span hidden size. So this is a parameter that we choose, hyperparameter that we choose, and we can vary it. So the idea is that later we split them along the last dimension to get separate encodings of the size reader beam size, sequence length, and our span hidden size, and another similar representation of reader beam size, sequence length, and span hidden size. So each of these tensors here are the representation of our start tokens and the end tokens. So in each of, if you see the length of both of these vectors is sequence length. So what it is telling us is that what is the chance of total as being the start token of the answer, and what is the chances of total as being the end of the answer of the question, what are the rocks. So how do we get the representation for the start token? uh, Technically in code it is done in a different way. We'll discuss this in a little bit, but first to get the mathematical notation down. So h start here is the BERT reader given the question NB, which we did tokenization in this way, and the position of the start of the span, and similarly h end is the BERT R Q comma B end of S. Okay, I know this is confusing, but what does this mean? It means, so let's say we want to know what is the probability of okay, let's before we talk that. And so the probability, so the reading, so the scoring function that the reader gives for a particular pair of B, S and Q is MLP of H start concatenation with H end. So what they're saying is they'll get representation, these two representation, H start and H end, they'll concatenate them, pass it through a matrix, add a non-linearity, and that should give us the value of the reader score for a particular pair of a passage and a span in it for a given question. Sounds easy, but that's how the equations are written. But if you see the code, there's a difference in how this is achieved actually in code. We'll discuss that shortly. And also in one more thing, they don't really do concatenation in the paper, they do an addition. I guess that makes it easier and keeps the number of parameters low also. Continuing on how this is implemented in real world. So let's take the same. So till now what we understand is how we get the S read score for one particular span. But in code implementation, we don't really do things for one particular span. We do it for the entire all these spans. So what happens is, let's say we continue with the same example. I am Akash, and we saw that it has a total of 1, 1, 2, 2, 2, 3, 3, 1, 2, 2, 3, and 1, 3 as the possible spans here, right? So what we do is we create a tensor which we call candidate starts and candidate ends, which basically shows what are the possible values of the start tokens and what are the possible values of the end tokens. So this will be 1, 2, 3, 1, 2, 1, and for the possible ends it will be 1, 2, 3, 2, 3, 3. So now that we know what are the possible starting and end of the spans, we have to get the probability given to these particular tokens. Probability will be the wrong word. The logits given by the model as the start or the end of this particular token. So what we do is we do a gather. So for candidate starts, we do a gather from the start token representation, which is of the size RBZ, reader beam size, comma sequence length, comma span hidden size. And for the candidate ends, we do a gather from the end token representation, which is of the size, reader beam size, sequence length, and span hidden size. So when we do this, we get a tensor of shape, reader beam size, comma, total number of spans, total spans, and span hidden size, and reader beam size, number of spans, and span hidden size. So what do both of these tensor actually contain? So the tensor here, this star token represents all the possible star tokens, and this tensor here represents the logits for all the possible n tokens. So which is something here. So all the possible. So here we calculated for one particular span, right? So one particular span's start and end. This here is for all the spans, all the start and end spans. So here what we do is we each so this will be our h start of s1, right, and this will be h end of s1, and similarly we'll have h start of s2 and h end of s2, and this goes on for all the total number of spans that we have in the model, right? H start is number of spans, and h end the span number of spans. So in paper that they had mentioned that they technically do concatenation in the mathematical equations, but technically in code implementation they have just added it. So when we do an addition of this, what we get here is the representation of the representation for each of the tokens for each of these spans, and once we have representation for, let's say, hs1 and hs2 for hs number of spans, we multiply this with a trainable vector here and add some nonlinearity to get the s read bsq for all the spans that are possible, which is the number of spans here. I know it was a little bit confusing here, but I thought I should add this detail because it will make it is help in understanding the paper better. So let's talk about cost function. Now that we have done talking about architecture, we have to understand what is the cost function that is used to train here. So before we talk about cost functions, which we know is marginal log likelihood, but we have to understand what is the probability of a single span. So probability of a span in a particular block given a question Q is mentioned as the exponential of the reader score that particular block and span got for a given question, divided by the exponential of this reader value for all the blocks and all the possible spans that are present in the reader beam size, that is the total number of documents that we retrieve. So summation over b dash here belonging to the top k. So one interesting thing that we have to keep in mind is that here it is written as top k, but this top k is actually the reader beam size in the model, and for all these spans that are present in a particular block. So this is the probability of a single span, and it's like literal probability what it should be, like what is the value that this particular span got divided by all the other possible values that are there. So what is our cost function? our cost function is marginal log likelihood, which we represent here as L full, which depends on the question answer pair, and it is minus log of marginal probes. But here there is one extra thing that we have to consider while including marginal probes. So we have to keep in mind that here we're trying to predict a span, and uh, the target span can be present in different positions in the same block, or it could be present in different blocks also. So as a model, the job of the model is to predict the correct span. So the idea is that wherever, so let's say this was a B1 and B reader size, this is the total blocks that we retrieved, and the target span, the target answer, let's say here for the same question, what are the total number of blocks, the target answer 110 is present here, and it is present here also, and it's present here also. It won't be presented so many times, but the idea is that the job of the model should be to increase the probability that it gave to these spans for this particular question. So how do we write that? So that comes out as minus log summation over B given top K, which is the reader beam size here, and summation over all the spans belonging to B where the text of the span, whose definition which we discussed earlier, is equal to the answer. And wherever the answer is equal to the text of the span, we include those probabilities. Probability of that particular block and span given that question, which is this value here. Okay. Yeah, so I just wanted to point out here that as we discussed earlier, the same answer could be present in the answer text could be present in the same block twice, or it could be present in different blocks. We want to increase the probability of each of these possible spans that are out there, which are equal to the answer text. And yeah, this is the first part of the cost function. So there is another part here which we include as the aggressive learning part. Aggressive learning. So initially, when we initialize this task, there is a lot of chance that the retrieval model might not be doing well. Okay, so we want to encourage the retrieval model in the initial settings so that it learns more and more on its own, and it retrieves the correct answer. So how do we enable the retriever to do so? We set up a cost function that helps us in achieving that. So how do we do that? Before that, we need to discuss about what is the probability of a retrieve block. Probability of a retrieve block, just like we discussed about what is the probability of a span. So the probability of a retrieve block is the retriever's exponential of the retriever score. Exponential of the retriever score given to that block, given a question, given to that block, divided by exponential score of the exponential of the retriever score for all the blocks that are present in the top C, where B dash belongs to top C. Now top C and top K are different, so in paper they have set C equal to 5000. So what this means is, like, the retriever can retrieve almost 5000 top blocks, but only, let's say, top K here, which will be equal to the reader beam size, will be passed on to the QA model. What we want to do is, in each of these 5000 blocks that we are retrieving, we want to increase the probability, the S retriever score given to that particular block, which might have the target answer string. Okay, so let's say in the answer string 110 was present in 100 of the top 5,000 documents that we retrieve. So what we want to do is that we want to update the weights of the retriever in such a way that these 100 retrieved paragraphs get a better probability score here. So it sort of becomes like a classification task. So it's negative log likelihoods. So we represent this part of the cost function as the L early. Why we do this? Because they start the training method in such a way that for the first few iterations the only retriever part is learning, and when they think the retriever part is good enough and this L early loss decreases, then they start giving the input to the QA model. So L early is negative log of summation of probably P early here for B comma B given Q, the same probability for the blocks such that where B belongs to the top C retrieved documents, and A, the answer text belongs to the text of B, which basically means that if the target answer is present in that particular block, we want to increase the probability of that particular block, the probability that the model gave to that particular block. So the final cost function that comes out, which we write as LQ comma A, is the combination of L early Q comma A and the L full Q comma A. So as I said, initially you start training the retriever, and once the retriever is good enough, you start giving the inputs to the QA model, and at one point the retriever will receive gradients both from L early and L full. This brings us to the end of this video. It has been a pretty long video, but I hope you understood it. And if there are any questions, do drop a comment. I'll be very glad to help you on this. Thank you.